Okay, so today we're going to finish up really the culmination of the symmetry part. We applied symmetry to our wave functions. Well, before that, we applied symmetry to our molecules, found the point group, then we had the character table, and we spent a couple of days looking at the symmetry lines or rows in the character table to identify the symmetries of wave functions like molecular orbitals or vibrational motions with the arrows. And then today we're going to see how we use that to determine whether a spectroscopic transition is allowed or not. And so we're applying that to the transition dipole moment integrals for three-dimensional molecules today. So this is that bottom part of that whole point of the course is we start with that Lewis dot structure and we get all the way to spectroscopy. This is that last piece. And so we have, yes, it's not up. Okay, thanks. Okay, is that better? All right, good. Now, one thing I don't think I've mentioned, and it might have even been a problem on the homework about the total wave function being the product of all individual wave functions. That's been in the homework before. I don't know if it was in this one, but this is an important piece here. So for a molecule, there's lots of things going on in a molecule. You have nuclei, you have the vibrations, you have the electron cloud, you even have the rotation of the molecule. That's quantized too. And so the molecule can only rotate at certain speeds, which is bizarre, right? If you think about it, why can't a molecule rotate at any speed? Well, again, you're dealing with small atomic-sized things. They have wave functions associated with them. Even the rotation of the molecule has a rotational wave function. It can only rotate at certain speeds. And so these are the quantum numbers we would assign to those different things. You have the electronic wave function, the vibrational wave function, the rotational wave function, and then the nuclear wave function, which we don't deal with very much except in NMR. So the nuclear spin, the spin of the nucleus, would be part of the nuclear wave function. I'll go ahead and write these out. Electronic, I'll do vibe for vibrational, rotational, and nuclear. And so how would we determine the symmetry of the total wave function? The direct products. And so if we knew the symmetry of all of these, let's say the electronic one was A1 and the vibrational one was B1, and then the rotational was B2, and the nuclear was A1, then we would go to the direct product table for that particular molecule, and we could come up with the symmetry of the total wave function. And then we've talked about the direct product table being specific to the point group, and it gives the symmetry products of all of the character rows, those irreducible representations. And so that intensity is proportional to the square of the transition dipole moment. And so then if the results of the direct product does not contain the totally symmetric irreducible representation, or the top row of the character table, then that integral is equal to 0. And we would say that that transition is forbidden by symmetry. So this is a bit of review. We've talked about this for the particle in a box, but I'm just reviewing it for this set of notes. So if the result of the direct product table does not contain the top row, and I say contain because it might be plus, plus, plus. There might be several terms in there. If the top row isn't one of those terms, then that transition is forbidden by symmetry. So we use the Vesper theory to generate the geometry of the molecule. Then we find the point group using that flow chart. Hopefully you can move away from the flow chart. We'll let you use the flow chart on this first exam. But then later I want you to be able to determine the symmetry on your own by using example molecules in your head. So if you know that water is C2V if you can look at any molecule and say it looks kind of like water, it has the left and right side look the same, the front and back look the same, but the top looks different than the bottom, and it has a C2 rotation axis, I know that's what water has. And if I see that same symmetry in this molecule, then it's like water, so it's C2V. Ammonia would be C3V. So if you know that ammonia has that threefold character, then you might be able to see that in something like acetonitrile. It looks like ammonia with a nitrile stuck on the top. And so it should be the same symmetry as ammonia. So eventually you should be able to wean yourself off of the flow chart so that you can just know the symmetries of different molecules. It's going to be really helpful for you when you get into advanced inorganic or any of the other courses that you'll use point group symmetry for. So then if we have particular wave functions, that would be like the arrow diagrams. So vibrational wave function would be characterized by those arrows, the movements of the atoms. Or molecular orbitals, like the shapes of the electron cloud with the green and red colors. You should be able to find the symmetries of those. And then select that symmetry of the spectroscopic interaction. Well, for infrared, or I shouldn't say infrared, works invisible too. For direct absorption and for emission, it's going to be X, Y, or Z. So I'll go ahead and put those on here. So the Raman is all of those. And so if we want to determine the Raman selection rules, we have to use all of those rows that contain any of the second order pieces of X, Y, or Z. Absorption and emission is first order. It's just a single photon. It's just using a single dipole. So that's what I mean by select the symmetry of the spectroscopic interaction. And then we've got all of those different pieces. So then you can use the direct product table for the point group to determine the symmetry of the transition dipole moment integral. And if that integrand has got an even function in it, then it's non-zero. So let's flash back to the 1D box problem. We only had one axis. Here's our character table, CI. We label everything with AG and AU. And so those are the symmetries of our wave functions. We can determine those symmetries using this inversion operator. So essentially, does minus x look like positive x? And so we centered these wave functions on 0. And so if the left and right look the same, minus x looks like positive x, then we have a +1 under inversion. And if they are opposite of each other, we have a -1 character. Okay, so we can look at those under inversion and label them accordingly. And so then we have this symmetry set up. So this is the transition dipole moment integral, and problems 9 and 10 on the homework are asking about the symmetry setup. Okay, and so we're looking at direct absorption, say from AG to AU, using X, Y, or Z light for direct absorption. So we come up here, this is going to be the middle piece of our symmetry setup. And so from wave function 1 to wave function 2, using X polarized light, we have this symmetry set up. And so that's what that problem's asking. You have 4 or 5 choices of different direct product transition dipole moment integrals, and you just have the symmetries put in there. Now put these direct product times signs in there, but you could also just use the vertical bars. So in this case, the vertical bars are not really they're not absolute value of x. They're just meant to signify the direct product. Okay, you can write it 2 different ways. And then we can use the direct product table to simplify or produce the following steps. And so AG times AU gives you AU. And so then you simplify that, and now you have 2 terms times each other. And then you can use the direct product table again, and come up with AG. And so then that integral is going to be non-zero because that's the top row in our character table over here. Is equal to AG. And so this means that 1 to 2, the transition from 1 to 2 is allowed. Notice how as long as you have 2 of these AUs in here and 1 AG, the odd nature of these are going to cancel each other out. It's like having 2 minus 1s in a product. If you have 2 minus 1s, they're going to multiply and give you a plus 1. And then you can have as many plus 1s as you want. As long as you have an even number of minus 1s, then they're going to eventually cancel each other out. And so that's what you would have if you were going from this one to this one, right? AU to AG. X is still odd, so X is here. So whether the AU is on the left or the AU is on the right, it doesn't matter. It's going to cancel. And so this is, you could make this a really general solution. 1 to 2 is allowed. That's specifically what we solved for. But you could show that as long as you're going from a U to a G or a G to a U, then it's allowed. So then you could start building up your symmetry selection rules. And we know that plus or minus 1 is allowed. We've shown that. Because plus or minus 1 gives us always a U and a G. And then light is odd. So an odd light symmetry will allow us to go from a G to a U or a U to a G. What about an AG to an AG? So this one here, what's the symmetry setup for that one? AG for the top state, AU for light, AG for the bottom state. Now we have just 1 minus 1 in there. And so that's going to poison the whole show because we have an odd times an even, which makes it odd. And then we have an odd times an even, which makes it odd again. So our result is going to be AU, which is equal to 0. So going from AG to AG is not going to work. So that's a delta N of 2. What about an AU to an AU? So what about this one? The symmetry setup for that is AU for the top, AU for light, which is the x-axis, and AU for the lower state. And now we have 3 minus 1s, and you know what that's going to end up with, right? Minus 1 times minus 1 times minus 1 is a minus 1. So an odd times an odd is even. That looks promising, but odd times even gives us odd again. And our result is odd, so that's equal to 0. So we can't go from AU to AU or AG to AG in this particular system. And so plus or minus 2 is out. And so is plus or minus 4 or 6 or 8. You can show by drawing a more energy levels and labeling their symmetries that delta 2, delta 4, all the even jumps are going to be forbidden by symmetry. And all of the odd jumps, jumping by 1, jumping by 3, jumping by 5, you can get the same selection rules. And that was a lot faster than going through that long transition dipole moment integral and getting down to the cosines and saying when I have plus 1s and minus 1s, I have 0. Okay. So let's look at the Raman setup. So we have those selection rules. Okay. Let's look at the scattering now. So scattering, you can do scattering when it actually matches one of the energy levels, but most of the time it's when light is between the energy levels. So light's not absorbed, but it does interact. So the wave function feels the electric field of this photon of light and interacts with it, but it can't absorb it because there's no level up there. But it can absorb part of the light. It can scatter the light and steal some of its energy. And so the incident light can come in, interact with the molecule, and be scattered off with a redshift. So a photon comes out with less energy than the photon that came in. And one conceptual way to think about this is the different axes or polarizations of the light. Like it comes in polarized on X and leaves with polarization on Y. And that would be the X-Y interaction. So that's why we have all of these twofold or second order interactions. Now in our particular case, we don't have a y-axis or a z-axis. So we don't have all of these, but we have x squared. So we can at least think about x squared. It's going to be the same symmetry setup no matter what, because all of these are on the top row. So all of these are going to be AG. But for our particular case, we want to look if Raman can cause us to go from the ground state to the first excited state. And so this would be the setup with the wave functions. We have quantum state 1 here, going to quantum state 2, and we're using the x squared Raman system. So we're scattering light along the x-axis. So we go and find all of our symmetries from the character table, and this would be the symmetry setup for this particular scattering problem. So we have AG, AG, and AU. Okay, it looks bad because I've got one AU. So already I'm thinking this is probably not going to turn out right. And so we go to the direct product table, and we end up simplifying the two AGs, and now we have AG times AU, which gives us AU. So it's equal to 0. So Raman cannot scatter light, and or this molecule cannot scatter light and end up in the first excited state. And so what scattering is allowed, it's allowed at that final state as AG. So we have this setup, you know, and we have, so this can connect our ground state to this upper level. And this is where we get our Rayleigh scattering. So if it goes up and all the way back down to 0, then we have a delta N of 0, which is Rayleigh scattering. So that's elastic scattering. And then if it goes up and comes down to that upper level, n equals 3, then we've changed by delta n equals 2, and that is allowed by Raman. And of course, we could have Stokes and anti-Stokes, so this could be plus or minus here, plus or minus 2, plus or minus 4, etc. If we had a molecule that was excited to the n equals 3 state, it could interact with an incoming photon and jump down to n equals 1. And that would be a change in minus 2. So delta n equals minus 2. And that's allowed as well. And that would be anti-Stokes. That's a really powerful technique because the light is blue shifted. And almost all spectroscopic, like fluorescence and phosphorescence and Stokes-Raman, are red shifted. So you have a laser line and you look to the longer wavelengths to detect your signal. But there's several phenomena that go on over there. You have fluorescence, phosphorescence, and Stokes-Raman. So all of those signals can be on top of each other. But to the blue side of the laser, the only thing that can be on the blue side of the laser is anti-Stokes-Raman. So we call that a zero background technique. Nothing about your molecule is going to be up there at the shorter wavelengths except for anti-Stokes scattered light. It's not a lot of light. It's a very improbable thing because you have to have the molecules be excited in their excited states. But if you do see it over there, it's very sensitive because you got just a little bit of light, but it's zero background. And so you can really see, the signal very well. So let's start doing the same kinds of analysis instead of a particle in a box. Let's look at visible spectroscopy, UV-Vis, looking at the molecular orbitals. And so in this case, we have a molecular orbital on ammonia, and this highest occupied molecular orbital has a symmetry of A1. And you should be able to look at that and see if I rotate it, if I rotate this by a third, right, I move one hydrogen into the other and so on, does the orbital change color at all? No. So that would be a +1 in terms of its character. And so here's your rotation axes, and you see that's a +1. You also can look at the reflections. If I reflect that in this mirror plane, it goes through the nitrogen and hydrogen bond. the left and right look the same color. That's also a +1, so you could go through and you could see that your reflection planes all have a +1. And so you would be able to just look at this orbital, hopefully, and say, yeah, that's going to be A1. You could also look at it and say, the left looks like the right, the front looks like the back, but the top is different than the bottom. And the top being different than the bottom would make it look like the z-axis. So the z-axis has a positive end and a negative end, and this orbital has a positive end and a negative end along the z-axis. So that helps you identify that it has a z Cartesian symmetry. So I'm just telling you different ways to find out the symmetry, what row in the character table this orbital is. Okay. And this top one is A1. Again, you rotate it, it's the same. You reflect it, it's the same. It's the same left and right and front and back, but the top is different slightly than the bottom. And so that would be A1. And so the question is the HOMO to LUMO transition allowed in this molecule? So can this occur through direct absorption? So direct absorption is going to use either Z polarized light or XY polarized light. Now, unlike our particle in a box, this has different rows for X and Y and Z. So we have two problems to do. We have the direct product using Z, and we have the direct product using X or Y polarized light. And so Z polarized light is A1, and XY polarized light is E. So this is the symmetry setup for both of those. And this is the question we're trying to answer. We have the highest occupied molecular orbital, that's a wave function, right? And we have light in the middle, X, Y, or Z. And then we have this wave function for the highest, the lowest unoccupied molecular orbital. And here's our C3V direct product table. So this is an interesting one. Remember, anything times itself gives you A1. So A2 times A2 gives you A1, right? But look at E. E is a two-dimensional row. And so if we take something of 2 dimensions and multiply it by 2 dimensions, we end up with 4 terms. 2 times 2 is 4. And so we have a single dimension term A1, we have a single dimension term A2, and then a 2-dimensional term E. So this is essentially like saying when you have these integrals and you have 2 functions times each other and they produce a sum, that's what's going on here. So this is a wave function with symmetry E times a wave function or a function with symmetry E gives you a sum of several terms. And that sum does contain A1. So that's why I would say contains the top row. There it is in that sum. And so let's look at this one. We have this XY polarized light, and here's our transition dipole moment integral. And here's the Z one. Actually, let's just do Z first because it's simple. We have A1 times A1 times A1. And we can look at that table. We're going to get A1 for the first pairing, A1 for the second pairing. It's A1 all the way across. So you know that it's going to equal A1 in the end, and that's not non-zero. So definitely Z polarized light can cause this transition to occur. So that's good. It's allowed by Z polarized light. But let's look at XY polarized light. We take E times A1, and we get this long result. Oh, no, E times A1 is just E. And then A1 times E is E. And so we end up with this integral over all space of E, which is equal to 0. So the HOMO to LUMO transition is allowed for Z polarized light only. And this will figure into its intensity. Now, we don't have our molecules, I mean, sometimes we do, like if we stick them down to a surface and they might be oriented, and we could send polarized light in, we could test this and it works out. But most of our molecules are in space, and they're like a molecule may be lined here and the light's coming in with Z polarized light that lines up with that molecule and can cause this transition. But the same polarized light for this molecule that's sideways, to that molecule, this would be X polarized light, and it wouldn't be absorbed. And so this kind of gives us 1/3 of the possible intensity that we would have for this transition. Since it's only allowed for one type of interaction with light, they've got 3 possible axes, and then only 1/3 of them will absorb it. Then our intensity is lower. The signal is going to be smaller. If it's allowed for everything, that's going to be a strong peak. So even though we can't calculate the intensity using symmetry, we can get kind of a rough estimate and say this would be a stronger transition than that one. If this one has X, Y, and Z polarized light allowed, then any kind of light hitting that molecule could be absorbed. But if only Z polarized light is allowed, then 1/3 of the photons are going to be possible for absorption, and the other 2/3 go right through. Okay. Let's look at rotational energy levels. So totally different type. We've done particle in a box. We've done electronic wave functions, the molecular orbitals. Now let's talk about rotational energies. This is the rotational energy equation. And here are the energy levels shown over here. And I went ahead and labeled the symmetries, and notice for rotational energies they alternate. Okay. And so they go from A1 to whatever the symmetry of that motion is. And we would take that, if we had a particular molecule, we could look at its character table and see where Rx, Ry, and Rz are. Okay, so if you notice there that the even quantum numbers are A1 or top row, and then the odd quantum numbers are whatever the symmetry of the motion is. We did this for water earlier. Okay. And so this is for rotation of water. Around the y-axis is B1. You can see that down here. Rotation around the y-axis in water, which is a C2V molecule, is B1. So that's where this B1 came from. And then we have the direct product table. I went ahead and filled out the whole thing instead of leaving it triangular. And so can this rotational mode be excited by direct absorption of light? So we have a point group of C2V. The ground state rotational wave function is A1. The excited state is B1. And here's your other rotational motions. We're going around Y, so it's B1. And so here's our setup for Z. We have A1 for the ground state, whatever the motion is in the excited state, and Z light. So we look those up in the character tables. Ground state's A1, Z is A1, and the upper state is B1. And so A1 times A1 is A1, B1 times A1 is B1, and so we have the integral over all space of something that's not the top row. So that's equal to 0. So Z-polarized light cannot cause this transition. What about X-polarized light? Notice in this character table, X, Y, and Z are on different rows. So X is B1, which is going to turn out to be a good thing. So A1 times B1 is B1, and then B1 times itself is A1. So we have the integral over all space of something that's top row. Oh, I screwed this up. I put a slash to that equal sign. That is equal to 0, not equal to 0. Okay, it's this one. The top row is not equal to 0, so that's allowed. Okay. And so then what we'll notice is in vibration, and rotation, light that matches the symmetry of the motion can be absorbed. Okay, so this is a conclusion. If we notice here, the Z polarized light did not match the symmetry of RY. Do you see that? The Z polarized light was A1 and RY was B1. Whereas over here, X polarized light was B1 and RY was B1. And so since this works out that every other level is either A1 or the motion of the molecule, we're either starting in A1 or ending in A1. So we're always going to have an A1 and the symmetry of the motion. And so we need a piece of light that's going to cancel out the odd character of that motion, or be able to interact with it is another way to think about that. And so we can simply look at this table and say for rotation around Y, X polarized light can be absorbed. I already know the answer. Okay, I may still be asked by DW to show the work, right? But I know X is going to be the one. And since R, Y, and Z are on different rows, it's not going to work. Okay, it's not going to end up with a non-zero result. What about rotation around X? Which kind of light would allow rotation around X? Here's rotation around X, and here's Y polarized light. So for this molecule, rotation around X would be absorbed by Y polarized light. And then rotation around Z has no light that will allow it to be absorbed. Yeah. Rotation around Z will not absorb any light is another way to say that. Yeah. Because Z and RZ are on different rows. Okay. Same thing will happen in vibration. So in infrared spectroscopy, because the energy levels alternate, whatever the symmetry of the motion is, that's the light that can be absorbed. So let's look at a vibrational example. So here we are in, I think it's the asymmetric stretch in water. Every other level is A1 and the other levels are B2. So the odd quantum numbers are B2. So that's the symmetry of the motion. And we can set this up like if we had this one, that's A1. I'll put a question mark here in B2. So no matter which, whether you're going from 0 to 1 or 1 to 2 or 2 to 3, one of those is going to be B2 and the other is going to be A1. And so the thing in the middle needs to be B2 for this to turn out to be non-zero. Okay, I see some nods. That's good. So let's look at that now. Let's do the work. Okay, so we have this asymmetric stretch, which has Y symmetry, because we went through and did the canceling arrows a couple of lectures ago, and we determined that that was Y symmetry. So down here we have Y symmetry, which is going to be B2, and so that's going to be that symmetry of that motion here. Y symmetry is going to give us B2 in both of these transition dipole moment integrals. And then we have here we're trying Z polarized light. Z polarized light is A1. And so we have A1 times A1 gives A1, and then A1 times B2 gives B2, and the integral over all space of B2 is equal to 0. So that's not allowed with Z polarized light. But when we're going to a transition that has Y symmetry and we use Y polarized light, then we end up with a couple of B2s in that integral. Just like we had 2 minus 1s and they cancel, now we have 2 B2s, they cancel out to give an A1. And so then we end up with this result that contains the top row, and that's not equal to 0, so it's allowed. So because those energy levels alternate in their symmetry, this is what allows us to sort of cut to the chase in this character table and say for direct absorption, for vibrational motion, and that occurs in the infrared region. That's why this is labeled IR. So if our motion has the motion of Z, so our symmetric stretch had a dipole moment that changed in the Z direction, then Z polarized light will cause it to be absorbed, or it can absorb Z polarized light. And then this asymmetric stretch is moving in Y, so the dipole moment is going left and right in the Y direction. We can find Y in that character table and know that Y polarized light is going to absorb, and it's going to be that motion is B2 and so is light and polarized in the y direction. We didn't do X because it's not going to yield anything, but let's go ahead and just for grins. The symmetry setup for X is going to be, let's go ahead and write it out, Y and X and A1. So our motion is B2, X is B1, and our lower state is A1. So A1 times B1 is B1. I don't even need the direct product table for that because anything times A1 is itself. So A1 is kind of like plus 1. I'm multiplying by plus 1. Okay. And then I have B1 times B2. Now that one I'm going to have to look up. Okay. So I go over here to the direct product table and I have B1. Let's see where my pen go. Okay, I have B1 times B2. So that's this one right here. So A2. I've never gotten that before, not in any of these problems. And so I look at that and I say, it's not A1, it's A2. That's not the top row. So this one's equal to 0. Okay. Don't get fixated on the A. Right? Go at least to your character table and see that that's not the top row. Okay, so that's all of the symmetry setups. That's practicing vibrational motion, molecular orbitals. We even did the particle in a box. And you can kind of see now why we like this as chemists, because it's so much easier than going through the whole transition dipole moment integral. Now, next time we will go, we're going to have Labor Day on Monday. So then Wednesday, we will go through a little bit more practice on identifying the symmetries of molecular orbitals. So all the greens and red clouds, that's the most difficult one. I think the arrows are easier than that. And then I'll give you some more review and answer questions for the exam. Okay. Well, we've got plenty of time now, so if you do have questions on the homework or whatever, you can stay and ask, and the rest of you can go.